Despite centuries of scientific contributions and the development of technologies like those that you are about to see, many unanswered questions still prevent us from fully understanding the complexities of our universe. What is the universe made of? How do we make energy storage more efficient? What causes metal to fatigue and fail? What makes one virus deadlier than the next? Students and staff here at the Cornell Laboratory for Accelerator-based Sciences and Education, or CLASSE, have been pursuing these questions for more than 50 years, developing new technologies, pushing the frontiers of science, and improving the lives of millions. To do this, we have designed one of the most powerful particle accelerators in the world, right here in the Wilson Synchrotron Laboratory. The accelerator complex creates electron and positron particles and accelerates them to near the speed of light. Initially designed to smash these particles together, it is now finely tuned to generate an intense beam of light that is used to study matter at the atomic scale. This light is called synchrotron radiation. 40 feet below the Cornell campus, positrons are created and pulled into a linear accelerator, or LINAC, where a driving radio frequency is timed to energize and accelerate the particles in a straight line. Once the positrons leave the LINAC, they enter the booster synchrotron, which is similar to the on-ramp of a highway. The positrons travel through radio frequency cavities where they interact with radio waves, getting hurled forward faster and faster until they approach the speed of light. When the positrons reach the desired energy, bunches are transferred into the particle superhighway, the Cornell Electron Storage Ring, CESAR. Electromagnets steer and focus these particles into a circular path, while waves push them like surfers on the ocean. In CESAR, they travel around the half-mile ring at a rate of 400,000 times every second. Special magnets, called undulators, subtly disrupt the path of the positrons as they travel through CESAR. This disruptive process results in the emission of an intense beam of light. The light, in the form of X-rays, is directed down a separate beamline while the positrons continue around the storage ring. Beamlines and experimental stations called hutches make up the research facility called the Cornell High Energy Synchrotron Source, CHESS. A variety of optical instruments, such as beam splitters and mirrors, are set up along the beamline to adjust and focus the path of the X-ray in order to create the desired characteristics necessary for each experiment. CHESS X-ray beams are about 100 million times more intense than those produced by X-ray machines in a medical doctor's office, and can be used to image materials at the nanometer scale. Scientists come from all over the world to examine their samples with our X-rays. They might bring artifacts, protein crystals, batteries, solar cells, artwork, or other materials. When the X-rays hit a sample, they are either absorbed or scattered. A state-of-the-art detector collects and records the scattered X-rays coming off the sample. And from this information, scientists can learn about the structure and elemental composition of the sample. They can follow how the sample changes under intense pressure and strain. This kind of information is extremely valuable in understanding the world around us. There are more than 60 synchrotron radiation facilities worldwide. However, there are only 5 like ours. In a few moments, a guide will take you to visit the CHESS beamlines, where you will learn more about the variety of research initiatives conducted at the lab. During your tour, you will visit the CESAR tunnel to view the synchrotron booster ring and CESAR storage ring, highlighting different types of magnets and radio frequency cavities. You may also tour our new prototype accelerator. C-Beta is the most ambitious prototype of an energy recovery LINAC, or ERL, to date. ERLs are a new style of accelerator which promise high beam power while requiring little energy to run. This concept was invented and developed right here at Cornell. Let's begin the tour. But first, particle accelerators, when operating, produce high levels of radiation. Don't worry. The accelerator is now shut off for routine maintenance and tours. And just like your microwave at home, when the accelerator is turned off, the radiation is turned off. Cornell and New York State regulations require that each tour group carries a dosimeter capable of recording minute amounts of radiation. The reading on the dosimeter will remain the same throughout the entire tour. Your safety is our first priority. Once again, we'd like to welcome you to Wilson Lab. We are delighted to have you join us on the journey to better understanding our universe. Please enjoy your tour.